So it shows how the major species like hydrogen, CO, CO2, H2O, they vary. Okay. So this will come after, I mean, once you get the output. So and the code is here. So I think these files are, this .for files are the photod files. So these are sort of pre-compiled. So if you use this button, I mean this exe file, this is the exe. So I think this will work. Or these are the photon file, one can compile again. Okay. And what this tells you exactly what is coded there. For example, how all the algorithm, and this nothing but the theory that is being covered in the class. So this has all the algorithm that is covered, all these mechanisms and all these details. So we are not going through this one, but what we can do, we can, so this will open up a window like this, which is blank. Now once you go to file, and let's say I want to see the UV frame parameters, and this will show you what are the parameters. Is it visible from the back? Yeah. So it's a shows you the properties constant volume adiabatic flame calculation for a specific fuel. And what is the fuel? You have, it's essentially C8H18. It's a higher order hydrocarbon fuels, and there is no oxygen, no nitrogen. So it's kind of, once you write down that, you can see what it is going to be, and the equivalence ratio is above stoichiometry. Okay. And then product temperature is 2000, this is a initial guess. So it will converge to a actual calculation, and these are the pressure under which the reaction or this calculation is carried out. So one can vary the pressure and see how the, I mean your all this temperature or the reaction mechanisms, how they get affected because of the pressure. So it's called the pressure dependency. So that you can check. Then the enthalpy of the reactants per mole, this is a theoretical value which is typically available in any standard combustion book if you have a standard hydrocarbon fuel or standard fuel. Okay. And then these are the molecular weight and these two parameters. Once you get this, and if you do save and run, this will give you the output. Okay. So this
in that file you can change any value.
Yeah. So you see that what is your input parameter, that will again show up, then actually it shows the exactly the temperature what is going to be coming out after the combustion takes place. Okay. And now this will change, let us say I will make it 0.7, something like that. Now you see this particular temperature, this has come down, and previously you see the temperature. So once you make changes there, these things will, these are the output actually, and these are the input you have provided. So output it keeps on, I mean it will change, especially the change is the immediate change you can see in the temperature, because once the reaction takes place, these are pretty much exothermic reaction. So the output will be changed, and obviously the enthalpy change and all these things will be there. Okay. For example, let us say we change the pressure, yes, have combustion at atmospheric condition. You see the variation. Okay. And once you have this reaction at the, this file will contain all this data. So this data is this, not only this, also the mole fraction of different, I mean these are major species. Okay. So this will, and the output is written in a file, this output.uv, which is here, this one, this is the output file. Here you can see I have changed the pressure to 1 atmospheric. So, this is what it is there. So, every time I make any changes in the input file, once you run, this file will be kind of updated. So, you can always transfer this file if you keep on changing parameters, and then once you gather a kind of a series of parameter for say different equivalence ratio, then you can see how they vary, the plot that we opened up earlier, this plot. So, you can prepare this plot. Now, you can change the, let us say you fix your pressure, you fix rest of the parameters which are kind of thermodynamical parameters, you changing the equivalence ratio, then you see the how the mole fraction changes and the equilibrium temperature changes. Okay. And typically once you do that, and also one more thing, this is for a particular hydrocarbon fuel, let us say I can change the fuel parameter, I can also do that. Yes, I will do it for methane, which is more convenient to absorb. Okay. So, this is in atmospheric combustion. This got updated. You see the I have changed the fuel. So, this is CH4 and the temperature and all these things are getting changed. So, you get these parameters for plotting. Okay. So, this what it gives you, that once you change your input file, you can get series of this calculation done and prepare this kind of plots. And so, one can prepare this kind of plot and the behavior of this mole fractions and the temperature. And typically what you will see or observe that around the stoichiometric, that is 1, there is a peak, and after that it will start kind of decreasing. So, pretty much for all the hydrocarbon fuel you will see there that kind of nature, like going up from the lower equivalence ratio to the somewhere close around 1 and then coming down or starts dropping towards the end. But the behavior will be quite different once you go from, but while doing that it is kind of, you want to see these changes, then it is better to keep rest of the parameters like pressure and other parameters constant and then check. Then you see that how this behavior changes, and this is for I think heptane. So, once you start doing methane, methane curve will show more nice kind of a parabolic nature. But once you go methane to propane, butane and like that, then the post stoichiometry it starts slightly flattening up. Okay. And the reason I think you will cover or I can tell them. So, it has become more stoichiometric, that either you have, it is only one important thing, or the thing that message comes out that it is not a complete combustion. Okay, once you go higher and higher because of certain conditions, equivalence ratio is higher, then either you are running out of fuel or you are injecting too much of fuel or you are running out of oxidizer. Okay. So, it is kind of a, because of incomplete combustion, this shows you the temperature variation. Okay. So, this actually does this calculation, this is, then another file is that HP flame parameters. So, this again does the what is the fuel you are giving. So, it has C7H16, okay. And if you run that, it will again here is the output. So, for a specific equivalence ratio, fuel, pressure and reactant, you get all these parameters. I think these are different calculations for the equilibrium, right? HP flame, UV flame, they are the.
I think HP is
Yeah,
Any faster
volume.
So you can actually learn all the stuff we discussed using the software.
Uh, The third one is the TP calculations. So this is again for C8H18. So this, what is this TP is?
Yeah, I'm little confused. I have not done this one. I don't know what it means. Pressure and temperature are constant.
It could be. Yeah, you can actually, what you can, once you have this software, you can play around quite a bit, and also you will have at least the soft copy of the book. So you can see what are those parameters and then keep changing those and try out those things. Okay. And how these calculations are done for the adiabatic flame temperature or equilibrium flame temperature, I think that is covered in the theory. That can be, one can also kind of can do that calculation analytically. That means by using hand you can also do that. Okay. We'll take up some example like that in the discussion session and see how you can do analytically. Okay. So not only this particular software, but you can also use those your analytical stuff and do those calculations. So equilibrium calculation, adiabatic flame temperature calculation, these kind of a very standard things analytically one can do once you know the fuel and certain properties of the fuel. I mean, some information is required, molecular weight and those kind of parameters, then one can do those calculations. Okay. So anything else you want to demo? So that thing we will discuss, I think tomorrow in the afternoon session, in the last session I will do some more calculations like that. So meanwhile, I think, yeah, let's see, because this cannot be, I mean, we have to write so many things. So tomorrow only we can distribute those. Okay, I'm sorry about that. It should have been done. But then you can see tomorrow those hand calculations. Then probably once you go back and look at how these things actually done, hand calculations, software, how it does, and all this, and also you'll have access to the book. Okay. Any questions, that specific questions or clarification that you have?
Compatibility of this software.
Compatibility in the sense operating systems you are talking. Right now this is working fine in the Windows. This is running on Windows, so I think it will work because it's already pre-compiled that exe, but you also have the source code, that .for file, but you can also compile. But at least that exe will work, on Windows environment. That should not be problem.
Yeah, it won't work on
Mac.
Mac and Apple computer as such. Maybe you can use the Fortran files and then compile them.
Yeah, Apple it will work, Apple or Linux it will work because you have the source code also. So you have to compile that, then create the executable to run it. So input is not going to change, neither the source code is going to change. But here it's pre-compiled on the Windows based environment, so it will, I mean, it's easier to right now run and check. But you can compile the source code and then it will work. There should not be any restriction on OS or the architecture of the machine. It's a serial code, it's a Fortran file, that's it.
Sir, is it a freeware software?
This is not freeware. So if you buy the book, it's free. If you don't have the book, then it's not free. So it comes with the CD, the book.
Yeah, earlier, it used to come with the book, they attach it like a
CD kind of things.
CD kind of thing, yeah. Now, when you buy the book, then they give you access, you download.
Yeah, I think I bought this book almost 6-7 years back. I still have the CD, though I have not opened it up yet. Okay.
At that time, it was your CD.
Yeah. So this book is kind of I mean, if somebody is doing combustion and all these things, maybe a good book to start with. It goes very from the basics and into the deep of these things. And I think it's a very standard textbook for any undergraduate level or even in the postgraduate level to some extent for combustion.
Sir, online software is showing at ST273. That also giving me similar results. Can we rely on that?
Come again?
ST273. That is NASA code.
Mm-hmm.
I use generally that software for editing on this.
So, what do you think?
No, which I am thinking, I'm asking whether we can rely on this software, we can rely, so that we have to predict something, then only we will do experiments to get the value.
That's what I am asking your judgment. What do you think? Huh?
When you are using this software, how close is it to the actual scenario situations? Can you predict something about that?
Now, coming to that questions, like actual scenario, now this soft.
Or based on someone's mechanism?
See, this doesn't require, I mean, that kind of a mechanism, because it does the equilibrium calculation. So, equilibrium calculations only based on the global chemistry. That means, if you have, let us say CH4 oxidizer, it is going to give you CO2 H2O. Based on that, these calculations are done through iterative process. Now, coming to a realistic situation, first of all, we have to understand that part very clearly. In a realistic situation, you hardly can achieve an equilibrium situation. Okay, but for the sake of hypothetical argument, let us say I will set up some experiment in such that, and if I do equilibrium this thing, this would be close to that. And now, what the software is doing, there is nothing like a magic or miracle it is doing. What it is doing, you can do those calculations even in your hand. So, now it has to do something to his question also. What as the NASA site is doing all these things, they should be pretty much same, few digits or something here and there. Maybe it is predicting, for example, 301, that might be 300.5 or 301.5, something like that. Is that because it is coming, what architecture you are using, what is the background OS and the compiler, all this. So, it is a floating point digitization, that has nothing to do with the numbers. For a designer, I think 301 is a good number, not that 0.5 or 0.8. And those calculations is not something is magic, it is all handwritten calculations. So, this is not a software which is doing really hard coded combustion calculation. This is something more like a demonstration thing and a simple calculations which parallelly you can do by your hand and you can cross check what it is doing. So, those algebraic equations are only coded in this particular program, nothing else. So, that you can write your own MATLAB script, you can write your own other programming script, there is no harm, probably that will predict the similar things, as long as you are doing it correctly. Okay. Now, just to extend little bit, in a class, whenever we teach these things in a regular semester class, this is kind of a given a exam problem. They can find out all these parameters by hand calculation in an exam problem. So, now you think about it. So, what it is doing? It is not doing something really, I mean, rocket science. Okay. Does that answer your question?
Okay. Our initial prediction only one software, after that
Whatever initial prediction it is doing, you can check by your own calculation. Okay, whether correct or wrong, you will have your own answer. And any software, anything that you use in your life or whenever for design purpose, anything.
So when CH4 comes into the salt previously, and methane CH4 burns, the number of species, how can the software determine the number of?
The other case you are talking, right?
Methane or octane, any aromatic fuel, the number of species, how the software determines the numbers?
This one you are talking?
Yes, yes,
So, this species you are talking.
yes, yes, yes.
these things. Now, see there for particular hydrocarbon mechanism, you can have a, I mean the detailed options are there, I mean detailed mechanism is already understandable. So, when it is calculation is done, so this has already taken care of those things. Okay. So, that is why once you change that, because any hydrocarbon combustion, these are the standard parameters, because as Professor Agrawal was mentioning, this OH, CO, these are the all intermediate sort of species or radicals. See, CH4 bonds and it gives you CO2 or H2O, but it does not happen in a single step. It goes through all this intermediate process. So, now when you are doing those, I will say transferring your calculation to this code, either you can keep it or you can basically remove those for your calculation to make it simpler. Okay. So, this how many radicals you, and all these things are kind of having some importance, because more like once radicals form, that makes things move faster, because radicals are more reactive in the system. Any stable species won't burn in that way. So, somewhere it has to be those chains, I mean these chains need to be broken, they need to form the radicals, only radicals actually react, and they also die very quickly. So, those are called, I think you have covered that, the steady state, yeah. So, the radicals actually goes to that steady state, those things. So, they react, kind of absorbed, whether consumed or produced, then they goes off. But for,
methane burns in atmosphere, sir.
yeah,
Then here nitrogen chemistry is excluded.
nitrogen is kind of considered here as the inert product, a inert species. See, most of the time, unless you are looking at the NOx, which is NO or NO2 or something, nitrogen chemistry, usually nitrogen does not come into the reaction. So, nitrogen is kind of considered as the inert species, so that remain inert, it does not get into the reactions. Okay. So, those are pretty much any kind of calculation, unless you are doing very specific for the nitrogen based chemistry or something, that is remained there. But all these things up to the user, what you want, what is your requirement, based on that you have to make those changes. Okay.
I am asking for GRE 30 mechanism, for
Mhm.
this is combustion, this is a methane mechanism, sir.
Hmm.
There are 53 species like that. Another mechanism is available for methane, which
Hmm.
has only 34, 32. Which one is true?
That is a good question.
Yeah, I think this equilibrium, first of all, there are no reaction rates. So it's like, you are giving, very large amount of time for reactions to occur. So just based on the, equilibrium, what we discussed, this morning. So you have these equilibrium reactions, like, we were discussing CO plus 1/2 O2 CO2. So that's the equilibrium reaction. So it considers several of those reactions, but not like the reaction mechanism.
So,
Also the software, it has only limited species. If you use Chemkin, it has more species. Because Chemkin uses actually the reaction mechanism.
see, I will just I mean kind of add to that argument. See, these are things already written there board, now you just saw that. So, this is exactly what I was saying, that radical actually kind of gets reacted then absorbs. So, this means this goes to 0, means this is kind of equilibrium approach you are taking. So, you assume when methane starts burning, there will be some radicals like CO, H, OH, those kind of radicals, but though those radicals will take part into the reactions and then immediately they go off. So, this goes to the kind of steady state. Once this goes off, then you do those kind of a reaction which is coming from your equilibrium calculations, and then you equate and then finally do some iteration to come to that temperature. This particular equilibrium calculation does not account for any kinetics. Okay. Now, second part is that you ask that because GRI 3 having 53 species, 325 reactions, I can have some other mechanism, and some there are reduced mechanism. So, this is a quite always kind of a debatable issue. So, whenever see, whenever you go to real combustion calculations, theoretically, if you try to do with all these detailed mechanism, always becomes quite difficult when it's a practical problem you are dealing with. So that time people tend to go to the reduced mechanism, and there are, for specially methane, starting from global reaction, that is one step, there are 2 steps, there are 4 steps, there are 6 steps, 9 steps, there are different brand of, I think, the resume of reaction mechanisms available. Now, whether they are right or wrong, my quick answer is they are all right. But how do people testify that? When you do a reduction mechanism, that is a area of completely different area of combustion, that is called kinetics, chemical kinetics. You have a series of reactions and species, you choose something, then you go on reduction. So that is a group which actually does that. They go on reducing the mechanism. Okay, I cannot handle so much of reaction mechanism, I go on reducing that. And where I will stop, that has to be made some kind of, that is why they do some kind of experiment, try to get those data into the system and then match certain properties. And the properties which are for the premix flames, the very important property is the laminar flame speed. So they try to match that. When you go to the, say when you use a detailed mechanism like GRI3 and when you use a reduced mechanism like, let us say, 4-step mechanism, there will be variation in flame speed. And how much is that variation? There will be variation in the flame temperature. So always the adiabatic flame temperature, more you reduce the mechanism, the adiabatic flame temperature, which is essentially the temperature for the burn product, that will go up. That will be always higherly predicted. The reason is because you are now cutting off on your radicals. More you cut off the radicals, because there will be a lot of intermediate steps of the reactions which could be energy consuming. Now you have removed those things from your system, so more energy will be released, so your temperature will go up more. So more you reduce, that will happen. But then at the same time they look at it, the flame speed, and these are 2 important parameters. There are some other parameters also. Then by this kind of approach you go on reducing these things, and that is why those reduced mechanisms are quite tested. Okay. And the reduction process is done in that fashion. So it is not arbitrarily, one fine morning I wake up, I said, okay, there is a GRI3, I do not like this, cut off. I cut off some of this from, take it out, then I will just feed it into the system, okay, I am okay with my methane mechanism. No, that is not correct. It is going to give you all garbage. That reduction has certain procedure, it has to be properly followed, and then you come up with a particular mechanism which can give you proper adiabatic flame temperature, proper flame speed, then you say, okay, this mechanism is fine. Okay. That is why you come up with those reduced mechanism. And then combustion modeler, or they take up those reduced mechanism to do the real calculation. So it is a 2 different group who does the work. Okay. Any other thing? Any questions or anything else?